Let's talk about combination of springs. So let's suppose we have two springs, okay, of spring constants K1 and K2, and we connect them in series combination, right? So this is spring 1 having spring constant K1, then this is spring 2 having spring constant K2, and then so first spring is connected to second spring, the other end of second spring is connected to this block, okay, and the left end is connected to this rigid support. So this kind of combination is known as series combination. So what happens to the spring constant, or what is the effective spring constant of this system when we connect them in series combination? That's what we want to find out. Okay. So now let's consider the system like this, and suppose we pull this block, okay, we pull this block by distance x. So then suppose the displacement in the first spring is x1, displacement in the second spring is x2, okay. So the net displacement is x, that's equal to displacement in the first spring, which is x1, plus displacement in the second spring, that's x2, okay. Then we know F is equal to what? Minus kx, right? It is minus of k times x, okay. So the displacement can be written as what? F upon k. The displacement can be written as what? F upon k with negative sign, okay. So we can write here. So suppose the effective spring constant is k, okay, or let's call it k suffix s for series, because we have connected them in series combination. So suppose k, sorry, ks is the effective spring constant. So this implies that F upon ks, okay, this x can be written as the force divided by ks, okay, and you, if you like, you can put this negative sign. It's equal to x1. X1 is F upon, okay, F upon k1, plus x2 is F upon k2. Okay, you can put negative sign, right? So see, you can take F common and you can cancel it out. So you get this relation, okay, 1 upon ks is equal to 1 upon k1 plus 1 upon k2, right? So this is the effective spring constant ks for for series combination, okay. So the net displacement is x. It can be written as what? Force, sorry, the net force is suppose F. F can be written as what? It can be written as ks multiplied by x. So x can be written as F upon ks, right? So now when you pull this system with force F, then the force between these two springs is also F and F, right? So therefore the same force will be acting, same restoring force will be acting between these two springs. So this can be written as x1 can be written as F upon k1 with this negative sign, and x2 can be written as F upon k2, okay. Then you can cancel out F, so you get this relation. So what happens to the spring constant? Spring constants in series combination. So all the springs act as if, okay, I'm sorry, all the springs, they will act such that the effective spring constant is given by this formula. Okay, 1 upon the effective spring constant Ks is equal to 1 upon K1 plus 1 upon K2. If there are more springs, then it will be plus 1 upon K3, so on and so forth. So is this thing clear? Yes, no? All right. Good. So this is spring constant, resultant spring constant of the series combination. Then next, let's talk about parallel combination. Okay. So now suppose this is the rigid support and you have got two springs. Okay, you have got two springs. First one with spring constant K1 as before. Second one with spring constant K2. So they are connected like this. Okay, this is parallel combination, and the other end of both of the springs, it's connected to this block. Okay, and now suppose you pull this block. So now what happens? Okay, now what happens? So see, sorry. So now you apply some external force F. Okay, so this F can be written as what? See, there will be some force acting on first spring and some force acting on second spring. Okay, so when you apply an external force, both the springs, they are pulling the block towards left, right? External force is pulling towards right. Both the springs are pulling towards left. Okay, so there is some force in first one. There is some force in second one. Let's call it F1 and F2. So now in equilibrium condition, F1 plus F2 must be equal to what? The resultant force. Okay. So net force can be written as what? F equals to F1 plus F2. Okay. So now when you pull this block, both the springs will be pulled by equal displacement. Okay, both the springs will get pulled by the equal displacement. So this can be written as the restoring force in first one. It can be written as what? It can be written as minus of K1 multiplied by X plus restoring force in the second one can be written as minus of K2 into X. X is the common displacement of both springs, right? And now let's suppose this two springs, the parallel combination of two springs, it is equivalent to one spring. Okay, then the net force due to that one spring, net restoring force, will have this much magnitude F. Okay, and that can be written as what? Minus of K multiplied by, let's call it K suffix P, P for parallel. Okay, this is parallel combination, Kp multiplied by X. So now you can cancel out X here. So what do you get? You get the effective spring constant of parallel combination of two springs is Kp, it is just equal to K1 plus K2. Okay, and if there are n springs, then it will be just K1 plus K2 plus K3, so on and so forth up to Kn. So this is parallel combination of springs. All right, then so this is about series and parallel combination of springs. After that, let's suppose we have got a spring Okay, we have got a spring. Now, what will happen if you cut that spring? So what will happen to the spring constant? Spring constant. Okay. So in this case, please remember this thing, that the spring constant for spring, let's call it K. It's directly proportional to the area, that means the thickness, okay, of the spring, and it's inversely proportional to the length. Okay, so thicker is the spring, more would be that spring constant, and if longer is the spring, okay, weaker it will be, right? So spring constant, okay, spring constant is directly proportional to area, it's inversely proportional to the length. Okay, so if we remember this, then we can solve some nice problems. Okay, so for an example, let's suppose I cut the spring, I take the spring and I cut it in the ratio 2 is to 3. Okay, so I cut it from here in the ratio 2 is to 3. Okay, so this is 2, this is 3, right? So now what will happen? So now what happens is, so suppose this part, okay, this much part, now it has spring constant equal to K1. This part has spring constant K2. Okay, so how much is total length? This is total length. Okay, total length was L. So suppose initial spring constant was K. Okay, I'm sorry. Okay, initial spring constant is K. Okay, then since so you can say K is inversely proportional to the length. Okay, so K1 is inversely proportional to what? L1, right? So you can divide the second equation by the first equation. So what do you get? Dividing, you get K1 upon K. K1 upon K is equal to what? L upon L1. Okay, dividing this equation by this equation, you get K1 upon K equals to L upon L1, right? Because this can be written as this is equal to some constant upon L, this is equal to some constant upon L, and then if you take ratio, you will get this equation. Okay, so what's the ratio of length of L1 and L? 2 by 5, right? This is 2 parts, this is 3 parts. So how much is total length? 5 parts. Okay, so L1 upon L is 2 is to 5, right? So L upon L1 is 5 is to 2. So this is equal to 5 is to 2. Okay, and therefore you get K1 is equal to what? 5 by 2 times K. Okay, you get K1 equals to 5 by 2 times K. And by the same token, I can say K2 equals to what? It will be 5 by 3 times K. Okay. So now let's do a little bit of practice. Okay. So now I'm taking the spring and I'm breaking it in two equal halves. Okay. So I will break it in two springs such that their length is equal. So the spring constant of first one is K1, spring constant of second one is K2, and original spring constant of the spring was K. So how much would be K1 and K2? Length becomes half. If length becomes half, what happens to the spring constant? It becomes twice. Okay. So K1, because it is inversely proportional to length. So K1 equals to 2K K2 is also equal to 2K, right? Okay. Next example. So this is a spring and I am breaking it like this. Okay. So this is 1 is to 4. This is 1 is to 4. So now tell me. So this is length of this part is 1/5. Okay. So length of L1 equals to what? L1 equals to 1/5 of L. Therefore K1, it's inversely proportional. It is equal to 5 by 5 times K. Okay. And L2 is how much? It is 4/5, right? It is 4/5 of the total length. So this implies that the spring constant of this part, it is equal to what? 5 by 4 times K. Okay. Just invert this. Let's take one more example. Let's take one more example. So now suppose we break it in 1 is to 2. Okay. This is one part. This is two parts of the total length. So L1 equals to, you can say, it is 1/3, right? These are three parts. Okay. So it is 1/3 of L. Therefore, K1 equals to 3 times of K. Okay. And this is 2/3. L2 equals to 2/3 of L, and therefore K2 equals to what? 3 by 2 times of K. So now let us solve some problems based upon what we discussed yesterday at the end and this thing. A pendulum is hung from the roof of sufficiently high building and is moving freely to and fro like a simple harmonic oscillator. The acceleration of bob of the pendulum is 20 meters per second squared. Okay, acceleration is given at a distance of 5 meters. So distance is given. Okay, from the mean position. The time period of oscillations is very simple, right? Just use A equals to minus omega square x, but we just want magnitude. That's why I'm writing A equals to omega square x. Okay, so it is 20 equals to omega square multiplied by displacement is 5. Okay, that means omega square equals to 20 upon 5, that's 4. So omega equals to 2, and we want time period. So this is 2 pi upon t equals to 2. 2 gets cancelled. T equals to pi is the answer. Body of mass m is attached to the lower end of a spring whose upper end is fixed. Okay, the spring has negligible mass. When the mass m is slightly pulled down and released, it oscillates with time period of 3 seconds. So time period is 3 seconds. When m is increased by 1 kg, then period of oscillation becomes 5 seconds. The value of m in kgs is, okay, so when m is increased by 1, t becomes what? 5 seconds, right? So we have t equals to 2 pi square root of m upon k, right? This formula we have. So t1 by t2, I can say t is directly proportional to root m. So t1 by t2 equals to m1 by m2. Sorry, root of m1 upon m2. So at first you have mass m only. Second time you have m plus 1 kg. Okay, m plus 1 kg, right? So then we can square this. So this is 3 by 5 equals to root m upon m plus 1. Squaring this, we will get 9 by 25 equals to m upon m plus 1. That means 9m plus 9 equals to 25m by cross multiplication. So 9 equals to 16m. So m equals to 9 upon 16. Okay. So it's option D. Alright. Next question. So the period of oscillation of a mass m suspended from spring of negligible masses T, if along with it mass m is also suspended. So now mass is made 2 times. Okay. The period of oscillation will now be. So this is simple. It will be root 2 times T, right? Because T2 by T1 equals to what? So because T is proportional to root of m. Okay. So we can say it is m2 by m1. It's equal to root of m2 by m1. So that is 2m upon m. So this thing will get cancelled out, m and m. So T2 equals to root 2 times T1. Okay, option D. A simple pendulum performs simple harmonic motion about x equal to 0 with an amplitude A and time period t. Okay, amplitude is given, time period is given. The speed of pendulum at x equal to a by 2 will be. So speed is given by omega square root of a square minus x square. Okay, omega can be written as 2 pi upon t. Okay, and x is what? Because there is t in all the options. Okay, so a square minus x square, which is a by 2 square. So it is a square minus a square by 4. Okay, so it is 3a square by 4. It's 2 pi divided by t. So if you take square root, you get v equals to 2 pi upon t multiplied by root 3a upon 2. 2 and 2 gets cancelled. So it is root 3 pi a upon t. V is option C, right? Okay. So question on spring constants. A spring of force constant K is cut into lengths 1 is to 2 is to 3. Okay. So it is cut into lengths 1 is to 2 is to 3. They are connected in series and the new force constant is K prime. Okay. So see, this is your spring. You cut it in the ratio 1 is to 2 is to 3. Right. Suppose this is 1 is to 2 is to 3. So this is K1, this is K2, this is K3. Spring constant of this one is K1, K2, K3. So how much will be K1? So add this 3. So it is 1 by 6th. Right. This length is 1 by 6th. That means spring constant will be what? K1 is equal to, okay, you can say L1 equals to L by 6. L2 equals to 2L by 6. And L3 equals to 3L by 6. So spring constant is inversely proportional to length. So K1 equals to what? 6 times K. It is equal to 6 times K. Right. Okay. K2 equals to 6 by 2 times K. Okay, just invert this number. K2 equals to 6 by 2, that means 3, 3 times K. And K3 equals to 6 by 3, okay, that is 2, 2 times K. Is this clear? After that, you connect them in series. My question is, you break it like this, okay? You cut it and you connect it. So it's like it's like restoring the previous case. Okay, you take a spring, you cut it, and again you join it. There won't be any change in the spring constant. So I don't want to solve for series combination. K dash is just equal to K. Even if you solve, you will get same. Okay, using formula for series combination. Then K double dash will be equal to what when they are connected in parallel. So K double dash is equal to K1 plus K2 plus K3. It is 6K plus 3K plus 2K. 6 plus 3 plus 2 is 9 plus 2, 11. Right. So it is 11K. Okay. And then if you take ratio, K dash is to K double dash equals to K upon 11K or 1 upon 11. Right. It's option B. Next one, a mass of 2 kg is put on flat pan. Okay, there is a flat pan like this, and this mass is kept on it. Attached to a vertical spring on the ground as shown in the figure. Okay, then the mass of the spring and the pan is negligible. Mass of the spring and the span, it's negligible. When pressed slightly and released, the mass executes a simple harmonic motion. The spring constant is 200 newtons per meter. What should be the minimum amplitude of motion so that the mass gets detached from the pan? Okay, take g equals to 10 meters per second square. Okay, 1 minute goes in reading the question itself. Anyways, so what will happen? At what position will it get detached? So now suppose you press it and release. What will happen? There are two forces acting on it, right? There are two forces acting on it. One is the spring force, that's upwards, and another is gravitational force, it's downwards. Okay, so it will stay connected to the pan till the time both the forces are equal. I mean, the maximum spring force can be equal to the gravitational force, right? So you can say kx should be, okay, less than or equal to gravitational force. Till that time it will be attached. Once it exceeds the gravitational force, it will get detached from the pan. Okay, so k is 200. We want x only. Okay, so this is 200 times x is greater than or equal to mg. M is 2. 2 multiplied by 10. Okay, this is my x. Okay, so take 200 on other side. So it's 20 upon 200 is zero point 0.1. So x is greater than or equal to 0 0.1 meter. Okay, options are in centimeter. So you can convert this in centimeter. 0 0.1 multiplied by 100 centimeters. Okay, so it is greater than or equal to 10 centimeters. Right? Option A. A rectangular block of mass m and area of cross section A floats in liquid of density rho. If it is given a small vertical displacement from the equilibrium, it undergoes oscillation with time period t. Then, okay, so when you dip a block, okay, when you put a block in a liquid, okay, if it floats, that means its density is less than density of liquid, right? This is from Archimedes. Okay, so suppose we have this block, we are putting it in liquid, some liquid, and it floats. Okay, so suppose it's this much length gets immersed in liquid. Okay, this much length it gets immersed. Okay, so there is always an upward force acting on it due to the liquid, because of which it flows. And how much is that upward force? It is equal to mass of the volume of the liquid which gets displaced because of this block. Okay, this is Archimedes principle, Archimedes law of buoyancy. Okay, so now see, the upward force equals to force due to buoyancy. So the spelling is, I guess, Buoncy, right? And it is given by, it's equal to the weight of the liquid displaced. Okay, so how much is that? It is density multiplied by volume. So this much would be volume. This is suppose area. This much length is L. It is A into L multiplied by. So this is volume that is immersed in liquid. Okay, so that much liquid gets displaced. Okay, and the force due to buoyancy is equal to what? Weight of the liquid displaced by any solid. Okay, so this is volume. Volume multiplied by density will give us the weight. Now, on top of this, if you give a small vertical displacement, so if you push it further, what will happen? So you are pushing it, the water or that fluid, it will resist that change. Okay, so suppose you push it by displacement x. So now excess force due to buoyancy will be how much? So excess force due to buoyancy is equal to, I can say, let's call it F. It's equal to A multiplied by that displacement. Okay, this much is the extra volume that you are inserting inside the liquid multiplied by rho. Okay, and if the displacement is downwards, that force is upwards. That's why we can put negative sign like this. Okay, so now this is equivalent to, okay, F is proportional to minus x, right? More you push, more excess force will be there due to buoyancy. Okay, and because of that it will oscillate, right? So we want to find time period of that oscillation. So now time period of oscillation is given by 2 pi square root of m by k. And now what is k here? So if you compare this with f equals to minus kx, okay, if you compare this with f equals to minus kx, so k is equal to a multiplied by rho, right? So this term in multiplication with x, a into rho is equal to k. So you can put that and you get t equals to 2 pi square root of mass of the solid, okay, mass of the block upon a rho. So this is time period. Now you can tell, is it inversely proportional to root m? No. Is it directly proportional to rho? No. Okay, square root of rho? No. It's inversely proportional to root of rho. Is it inversely proportional to root a? Yes. Okay, it is inversely proportional to root a. So option C is the answer, right? Not option D. Okay, next one. Two springs of spring constant K1 and K2 are joined in series. The effective spring constant of the combination is given by. This is very simple, right? So option D is the answer. Okay, because 1 upon Ks is equal to 1 upon K1 plus 1 upon K2. This can be written as, so if you make denominators same, you have to multiply this by K2 and this one by K1. So it is K2 upon K1 K2 plus K1, and then you take reciprocal, so you get Ks equals to K1 K2 upon K1 plus K2. Option D. Next question. The time period of a mass suspended from a spring is T. If the spring is cut into 4 equal parts, okay, it is cut in 4 equal parts and same mass is suspended from one of the parts, then the new time period will be. Tell me. Spring is cut into 4 equal parts, right? 4 equal parts. So if you take any one of those, let's call it K1, it will be equal to what? 4 times K, right? Because it's inversely proportional to length, and you have T equals to 2 pi square root of m by K. This is the formula. Okay, so you can say T2, okay, or let's call it T1. So after cutting the spring and taking one of those parts, okay, then you get time period T1 equals to 2 pi root of m upon K1, which is 4 times K, so which is 2 pi square root of m upon 4K1. Okay, so you can take root of 4, that's 2, so you get 1 by 2 of T, or T by 2, right? 1 by 2 multiplied by 2 pi root of m by K. Sorry, I wrote 4K1, it's 4K. Right, so it is option C. Mass is suspend a mass is suspended separately by two different springs in successive order. Then time periods is T1 and T2 respectively. Okay, so time period, if you suspend it with this first spring, is T1. For second spring, it is T2. If it is connected by both springs as shown in parallel combination in figure, then time period is T0. The correct relation is, okay, let's find. So T1 can be written as what? 2 pi root of m by K1. T2 can be written as 2 pi root of m upon K2. And what about T0? T0 equals to 2 pi root of m upon, when you connect both of them in parallel, so net spring constant becomes K1 plus K2. So K1 plus K2, right? So then what we can do is we can square these, okay? So T1, right? So yeah, what we can do is we can write T1 equals to 4 pi square multiplied by m upon K1, or okay, or K1 equals to 4 pi square m divided by T1. Similarly, K2 equals to, okay, K2 equals to what? 4 pi square m upon T2. I'm sorry. Okay, then you can square this one also. So we get K1 plus K2 is equal to 4 pi square m divided by T naught. Okay, it's pi square. So you can substitute for K1 and K2 from here. Okay, in this formula. So what do we get? We get 4 pi square m divided by T1 plus 4 pi square m upon T2 is equal to 4 pi square m divided by T naught, right? So this 4 pi square m gets cancelled. 1 upon T1 plus 1 upon T2 is equal to 1 upon T naught. 1 upon T naught is equal to 1 upon T1 plus 1 upon T2. So it is option C, right? Yeah, matches with option C. Okay, just little calculation, right? Okay. Next question. Two masses M1 and sorry, not M1. Two masses. Okay. Two masses MA and MB are hung from two strings of lengths LA and LB respectively. They are executing SHM with frequency relation FA equals to 2 times FB. Then the relation LA equals to LB by 4 does not depend on mass. Okay, so does it depend on mass? SHM, you don't have spring, you have strings. Okay, so mass is hung with a spring, sorry, not spring. Mass is hung with a string and it oscillates like this. Then time period is given by what? 2 pi square root of L upon G, right? Does not depend on mass. Okay, it's not spring, it's a string. Okay, so it does not depend on mass. So these two options are not relevant. So FA equals to 2FB. Yeah. So time period is directly proportional to root of L, right? FA equals to 2FB. Okay, you want frequency. So frequency is inversely proportional. Okay. So FA equals to 2 times FB. Okay. It's inversely proportional to length. So you can say, okay, FA equals to some constant multiplied by 1 upon root LA. It's equal to 2 times 1 upon root LB because frequency is inversely proportional to root of L. Time period is directly proportional to root of L. Okay. So therefore you get you can square it. So you get 1 upon LA equals to 4 times 1 upon LB or LB equals to 4 times LA. Okay, or LA equals to LB upon 4, which is option A, right? It's option A, right? Bob of simple pendulum having length L is displaced from mean position to angular position theta with respect to vertical. Okay. If it is released, then the velocity of bob at the equilibrium position. Okay. So you have this angle is theta, this length is L, this length is L. Okay. So when this bob comes from here to here, how much will be its velocity? This is the question. When it is released, then velocity of bob at equilibrium position is. So you have to find this height. So velocity equals to square root of 2gh. Okay, I'm using, let's use small h only. Okay, so how much would be this h? It is this much length minus this much length. How much is this length? This length is, if you think about this triangle, okay, so let's call this A, this point B, and this is C, suppose. Okay, so we want length AB and this is D. Okay, so in this triangle you can say cos of theta equals to AB divided by AD, or it is AB divided by L. So AB is equal to what? L cos theta, right? So you want H. H is equal to L minus L cos theta, this length. Okay. So V equals to root 2 G multiplied by L minus L cos theta, or you can take L common also. If you take L common, it is 1 minus cos theta. It's option A. Time period of a simple pendulum is 2 seconds. If its length is increased by 4 times, then its time period becomes. This is very simple. T equals to 2 pi root of L by G. If length becomes 4 times, time period becomes twice because it is directly proportional to root of L, right? So length becomes 4 times. Okay. So let's say, I'm sorry. So T1 equals to 2 pi root of L1 by G. T2 equals to 2 pi root of L2 by G. And L2 equals to 4 times L1. So it is 2 pi root of, okay, 4 times L1 upon G. So take square root of 4, it is 2 multiplied by, so T is equal to 2 times 2 pi root of L1 by G. That is 2 times of T1. Okay, T1 is 2 seconds. So T2 is 2 times that, 4 seconds. Two simple pendulums of length 5 meter and 20 meter respectively are given small linear displacement in one direction at the same time. They will again be in phase when the pendulum of shorter length has completed how many oscillations? Okay, so this is a simple question, right? So the lengths are in ratio 1:4. Okay, so T is equal to 2 pi root of L by G. So T is directly proportional to, it's directly proportional to root of L. So T1 by T2 equals to root of L1 by L2. So it is root of 5 by 20. Okay, or 1 by 4. That's 1 by 2. Okay, so when okay, so T2 equals to 2 times T1. So when the first pendulum completes 2 oscillations, then second pendulum will complete 1 oscillation. And question is, they will again be in phase. Okay, that means if they start from same position, when will they come back at the same position? When the first pendulum has completed 2 oscillations, because only then the second one will complete 1 oscillation and come to the same position, right? So answer is option A. First one completes 2 oscillations. Mass M is vertically suspended from a spring of negligible mass. The system oscillates with frequency n. What will be the frequency of system if mass 4m is suspended from the same spring? Okay, so frequency, okay, frequency n is equal to, it's 1 upon 2 pi square root of k by m, right? 1 upon 2 pi square root of k by m, inversely proportional to root of m. So if m is made 4 times, right? M is made 4 times. So what will happen to the frequency? So n dash equals to 1 upon 2 pi root of k upon m dash, which is 4m. Okay, take square root. So square root of 4 is 2. It's 1 by 2 times 1 upon 2 pi root of k by m, which is n, right? 1 by 2 times of n, or n by 2. Let's see next question. If the length of simple pendulum is increased by 2%, then the time period. So very simple. Actually, we have seen this in units and dimensions. Okay, so t equals to 2 pi root of L upon G, or you can say it is equal to some constant multiplied by L raised to half. Okay, then therefore it depends on what? L to the power half. So percentage change, okay, percentage change in t is equal to what? It is equal to half of percentage error or percentage change in length. And how much is that? This is 2%. So it is half of 2. That's 1. Okay. It increases by 1. Right. It's option A. A simple pendulum with a bob of mass m oscillates from A to C. It oscillates like this from A to C and back to A, such that PB is h. This much distance is h. If acceleration due to gravity is g, then the velocity of the bob as it passes through B is. So very simple. Actually repeated. Okay. V equals to square root of 2gh. The body of mass 5 kg hangs from a spring and oscillates with time period of 2 pi seconds. Okay. If the ball is removed, the length of the spring will decrease by. Okay. So there is a body of mass 5 kg hangs from the spring, okay, with time period of 2 pi seconds. So we know t equals to 2 pi square root of m by k, right? M is 5. So t is 2 pi. This is equal to 2 pi root of 5 by k. Okay, so 2 pi gets cancelled. So 1 equals to root of 5 by k. That means k equals to 5. K equals to 5 newtons per meter. Then if this ball is removed, okay, the length of spring will decrease by. So now in equilibrium, what will happen? We can say that mg, whatever is mass is 5 kg only, mg is equal to, okay, the downward force is equal to upward force. So it is equal to kx. So put the values, okay. So 5 multiplied by g is 9.8. Yeah, but in options it is g by k, k by g. So let's keep g as it is. Okay, so 5 times g is equal to k times x, that is 5x. 5 gets cancelled, x is equal to g. So when ball is there, okay, the spring gets elongated by x. Okay, if it is removed, the length of the spring, it will decrease by what? It will decrease by x. Okay, x, which is equal to g meters. Option D. Next question. The second pendulum is mounted in a rocket. Its period of oscillation will decrease when the rocket is moving down with uniform acceleration, moving around the Earth in geostationary orbit, moving up with uniform velocity, moving up with uniform acceleration. So tell me. Okay, so time period is given by what? 2 pi square root of L upon G. Okay. And so you want time period of oscillation to decrease. That means now length is constant, length will remain as it is. The effective value of acceleration due to gravity. Okay. If it increases, then the time period will decrease. When will it increase? So see, the effective force, okay, the effective force on that pendulum, if it increases, okay, suppose this is a rocket and there is a compartment, okay, there is this pendulum here, okay. So what will be the force? So there will be tension in the string, okay, that is the force, okay, that is the force acting on that pendulum, and gravitational force mg downwards. So now see, so the tension will determine the effective value of acceleration due to gravity. Okay, so you want it to increase. So now that's why it must move with upwards acceleration. Okay, because then only this is tension. Okay, so then only you can say m into a, which is in upward direction. It's total upward force minus total downward force, that's mg. T is equal to ma plus mg, or you can say it is equal to what? M multiplied by a plus g. So this is effective value of the acceleration due to gravity which it will feel. Okay, so m into g dash you can say. So when it moves upwards with some acceleration, then only this g dash will be what? It will be greater than g. And when g dash is greater than g, in that case only time period will decrease. Okay, so don't get confused with T and T. This is tension, this is time period. Okay, is it clear? So it's option D. Next question. A simple pendulum is suspended from roof of a trolley which moves in horizontal direction with an acceleration a. Then the time period is given by t equals to 2 pi square root of L upon a dash. T equals to 2 pi square root of L upon a dash. Okay, a prime, where a dash is equal to. So yeah, this is also simple. So there is some horizontal acceleration a, and acceleration due to gravity is downwards. Okay, right. So again, what will be effective acceleration? What will be effective acceleration? They are calling it a dash. Okay, so a dash will be equal to what? I mean, a dash square will be equal to a square plus g square, right? So a dash will be equal to square root of a square plus g square. Okay, yes, it is option D. Got it? Yes, no? This is clear, no? The mass m is suspended from two coupled springs connected in series. The spring, the force constant for springs are K1 and K2. The time period of suspended mass will be, okay, coupled spring means they are connected, okay, they are connected in series, it's given, right? So in series combination, find out Ks, it is equal to K1 K2 upon K1 plus K2. if there are only two springs, okay, using this formula 1 upon ks is equal to 1 upon k1 plus 1 upon k2, right? So using this only we can find out ks is equal to k1 k2 divided by k1 plus k2, and time period will be equal to what? 2 pi square root of m by k, which in this case will be ks, the effective spring constant of the series combination, which is 2 pi square root of m upon ks is k1 k2 divided by k1 plus k2. So divided by k1 plus k2. Okay, k1 plus k2 is in denominator of denominator, so it goes in numerator. Right. So it is option D. Right, very good. It's option D. Okay.